Okay, well, thank you for having me. Here to tell you a little bit about some things that some physical models, we know string theory, supersymmetry, have taught us about how we think some more mathematical problems should behave or be thought about. So if this works. Okay, so I'm going to take you through first the motivation of the story. So I'm first going to link the notion of ADS-CFT, which is a notion in physics, to the correspondence between Sasaki-Einstein manifolds and Calabi-Yau algebras. Then I'm gonna ask our first question, which is how should we view the dual to these to non-commutative Calabi-Yau algebras in a geometric context? Then I'm going to define what we call a generalized geometry, which some of you might be familiar with already. And then I'm gonna do a small application of applying the generalized geometry to a question that we have, particularly in CFT. So the CFT side will be like the algebra side, and how that transfers over to the geometry side, which would be the ADS, to give you a bit of a feel of how we use this. And that's gonna bring in notions of GIT and moment maps, and I guess that's the part that's of interest to you. And then I'm gonna finish by asking you all a question, which hopefully will be helpful for both of us. I am a physicist, so I'm going to quote a friend of mine and say, some of this should be familiar. Please help. Like in general, we want to understand more about what's going on here, and obviously maths is the language that we use. So we're here to learn from you as well. So briefly, there is this thing called anti-de Sitter conformal field theory correspondence in physics. And it is just a physicist's way of describing the correspondence between a differential geometric and an algebraic geometric picture of a manifold with structure. So a manifold with structure for us would be a theory, basically, of a manifold that have fields on it. A Sasaki-Einstein Calabi-Yau algebra duality is, I think, more the mathematician's way of thinking about the same correspondence. And when I say Sasaki-Einstein, I really mean the Sasaki-Einstein thought of as embedded in a Calabi-Yau cone. And of particular interest to us today are going to be generalizations of Sasaki-Einstein spaces. Okay, so continuing on with the physics motivation, so how did this all come about? So in CFTs, we have these things called scalars, which are just fields in our theory. And we think of these as very, very large matrices. We have another thing in the theory that we call a superpotential, which is part of the big equation that defines how the energetic interactions happen in the theory. So if I take a simple example of what for us would be a simple example, then that would be n equals 4 super Yang-Mills. So some of you may have heard of super Yang-Mills before. It's just a type of theory that has fluxes on it, like similar to electromagnetism, but non-commutative. And n equals 4 just is the amount of supersymmetry. So it's an extra symmetry that's in the system. All that to say, it's just a model in physics. And we have 3 of these scalar fields. And this is the potential. As it's traced because we think of these things as large matrices in the standard way. Then this theory, this CFT, also has more than just conformal symmetry. So that's where the C comes from in the CFT. It also has supersymmetry. And supersymmetric theories are quite constrained in how they should behave in the vacuum state. So that's at the minimum of the potential. And that is to say that the scalar potential should vanish. So that's a potential that involves all of these fields. It's just a polynomial in these objects. It looks a little bit like this, where this is what we call the F term, and this is what we call the D term. And essentially the vanishing of this potential we call F and D flatness. Now the F term is given to us by varying the potential with respect to all of our different fields. And the D term turns out that it corresponds effectively to a moment map condition when we look at it in terms of the geometry. And we're going to look at how that happens in this talk. So again, back to a simple example, you had that potential that I showed you on the previous slide, and we take a derivative with respect to one field, and what we get is this constraint, if you like, on the theory to be in the vacuum state. And this is just a commutation relation. Okay. So effectively what we've got in the end is 3 fields, and they they you can think of them as coordinates, or equivalently as just forming like polynomials over C, and that they are commutative in the sense that they commute under multiplication of polynomials. And we call this the chiral ring. So it's just a polynomial ring with multiplication. If we then go down to the geometry side, which is the ADS side, we're looking at a dual geometry, which is a 5-sphere. And we think of it as a linked geometry in a Calabi-Yau cone. So the idea is, this is very pictorially, you have here a cone and you have an S5 as the linked geometry. And so the map goes commutative algebra or chiral ring of polynomials and 3 variables and S5 on the other side. In the maths, it appears that there is the same sort of idea, and that is defined, that was defined by Ginzburg in 2007, and it's what he called his algebras with potentials. So the way that he phrased it was that you would have a bunch of letters, which are just the phi's, and then you would form any word that you want with these letters, which are essentially they're going to be polynomials. And then you have a two-sided ideal that you modulo the whole thing by, and that gives you the algebra. And the aim of Ginzburg's work was to try and generalize the notion of a correspondence between polynomials or a commutative algebra polynomials and Calabi-Yaus as manifolds to non-commutative algebras. Please do as I say. Okay, so our examples go as follows. The n equals 4 super Yang-Mills. It was actually Ginzburg's first example in this paper. And I think we get very excited as physicists when a mathematician talks about what we do. And so this was his potential. And then you have the n equals 4 algebra and the dual geometry being the S5. So then we perform a deformation of this algebra. And in physics, what we do is we just add more terms to the potential and they mean something in the physics. And for the mathematicians, in particular for Ginzburg's purposes, this was just trying to generate a new kind of algebra. And in particular, if you define this potential, which in physics corresponds to an n equals 1 theory, if you set these certain constants to be particular, to have particular relations between each other, you get a non-commutative algebra that he called a Sklianin algebra, or that was known as a Sklianin algebra. And the question is, what is the geometry? And that's what we want to understand today. So first question, what is the geometry that is dual to a non-commutative algebra? And we think that the answer lies in string theory and in particular in generalized geometry. So we can use this to describe a geometry that's dual to these non-commutative algebras. And supersymmetry tells us that, well, there's potentially a notion of a Kobayashi-Hitchin correspondence, which I think that probably the people in the audience are more familiar with than I am. But essentially, it's the same idea as Atiyah and Bott's flat connection on Riemann surfaces, for example. And we can do this because we have an infinite dimensional moment map, as we will see. Okay. The next notion I'm going to introduce is the notion of R-symmetry. So these algebras will naturally have a grading that just corresponds to a U1 action on each of the individual letters. And in physics, this has a very specific meaning, and we call it the R-symmetry. And in this case, I've picked the same phase factor for each on this particular generator. But in general, I could choose any. So we could pick a candidate R-symmetry. In, again, taking the n equals 4 example, I could change by any phase here and then ask myself the question, which is the R-symmetry of my physical theory? And that is a very important question in physics, one that a lot of people have spent a lot of time thinking about. And we have found that in the CFTs, on the algebra side, this corresponds to maximizing a particular polynomial. We call it a-maximisation. So yeah, in the math speech, you can think of this as like a linearization of the U1 action on the Calabi-Yau. So what is the dual to a-maximisation in the geometry? And that's the example that I'm going to use to sort of illustrate my use for generalized geometry and implementing it in GIT. And a partial answer to this question was actually given by Sparks, Martelli, and Yau. And it's known as volume minimization. And so effectively what they have is this notion of taking the volume of the Sasaki-Einstein manifold, divide it through, normalize it by the volume of some S5 with similar dimensions or similar properties, and they maximize that in some sense. And we'll see in what that specifically means. But so all that to say, it has been looked at in the geometry before. Now, obviously, this is in sort of ordinary geometry. In the general case, it's an open question. And so this would be dual to a commutative algebra and blah. But this is a question that we're going to answer today. Okay. So yeah, this is just summarizing my questions. What I do want to emphasize, though, is that what I'm going to do today is a generalized geometry, but I'm not going to go to the full generalized geometry, which you need to understand the non-commutative algebras. So to do that, we would need to build a generalized geometry that we call exceptional generalized geometries, which are based on exceptional groups. Just because the formalism is clunky, and this is a 1-hour talk, I'm going to give you a truncated version of that, which gives you the dual geometry, which is the Sasaki-Einstein, so dual to commutative algebra. But all that you would need to do would be embed that in the corresponding exceptional group, and you get the full picture. So it's particularly, and just to know, in the a-maximisation question, it's particularly the d terms, banishing the d terms in the physics, that for us is going to correspond to this moment map picture. As I've noted before, you need to embed this in the exceptional group to see the full non-commutative story. And another thing to note is that this can be extended to more dimensions, but I'm going to look particularly at geometries of a Sasaki-Einstein 5, okay? So for a brief recap, what is a Sasaki-Einstein manifold in 5 dimensions? Well, you can think of it as the linked geometry of a Calabi-Yau cone, particularly where the metric is itself Calabi-Yau. So you have 2 structures, the holomorphic structure and the Taylor structure. The cartoon is back. And we can divide the tangent space on the cone into 2 parts. One, which is a 1-dimensional part, which is generated by a vector that we're going to call RdR, where R is some coordinate in the radial direction. And the rest is the tangent spaces to the Sasaki-Einstein, effectively. And I can use this vector field here, which is called the homothetic vector field, to generate some new structures. This is a contact structure. This is a holomorphic two-form, which is, or an SL2 structure that's going to descend to an SL2 structure on the Sasaki-Einstein. And this is going to be an SP2 structure on the Sasaki-Einstein as well, once it's pulled back. So you have an equivalent definition of a Sasaki-Einstein, which is given by structures that are really intrinsic to it, instead of thinking of it in terms of the cone, something embedded in a cone. And that is these conditions. So this is the compatibility condition between the Kähler and the holomorphic two-form. This is the sort of equivalent of the Calabi-Yau normalization. And then you have the Sasaki condition, an integrability condition on the holomorphic two-form, and the usual one on the Kähler two-form. And so a choice of this function R that I used to define this vector field RdR is effectively going to tell you which linked geometry you've chosen to describe your Sasaki-Einstein. So it's a deformation of the 5-dimensional manifold itself. And so if I choose sort of the one direction up here in green, then I'm going to get all the structures that are going to pull back to fixed link geometry. If I take a different one, R primed, then I'm going to get a link that looks more like this. And these structures will descend to some primed structures, if you like, on the link geometry. And the crucial part is that as far as the cone is concerned, these 2 choices of vector fields correspond to a diffeomorphism on the cone. But intrinsically, as far as the Sasaki-Einstein is concerned, it's a complex diffeomorphism, or complexified diffeomorphism. Okay. This one? Yes. So I think that the statement is that you can fix a complex structure, and then a choice of homothetic vector field is then a complexified diffeomorphism. Some of those may preserve your complex structure. Okay, so taking the tangent space of Sasaki-Einstein now, descending to the link geometry, I can again decompose that into two parts. And you have a one-dimensional direction, which is generated by what we call the Reeb vector field, which is what you get if you take the complex structure on the cone and you apply it to the homothetic vector field. And then you get the transverse direction to that, which is just a four-dimensional tangent space. We call this vector field the Reeb vector, and that for us is going to be important because it's dual to the R symmetry in the CFT. If I complexify the tangent space, then I get the following decomposition, and I can think of the Sasaki-Einstein in another way, in a third way. And this is the one that we're going to link to the generalized geometry. So this is really where I want to end up at, and that is in terms of the Cauchy-Riemann structure and a choice of Reeb vector field. So effectively, I can define a three-form in this way, and that will cut out a 0, 1 anti-holomorphic two-dimensional part of the tangent space, two complex dimensional part of the tangent space. And this is going to be involutive. And that, as long as this condition is obeyed. So this is the integrability condition on the Cauchy-Riemann structure. So this sigma is my Cauchy-Riemann structure. Then I'm going to have this condition, which I call the Reeb condition, for the sake of this talk. And keep in mind the factor of 3 either. And then this is the equivalent of the Calabi-Yau normalization. These three conditions are going to be the ones that I'm going to want to impose when I go to the generalized geometry. That's what everything's going to, the ones that we're particularly going to be interested in looking at. We'll say that way. Okay, so again, we're guided by physics. And so the cool thing that string theory does for us is that it tells us what sort of fluxes or what sort of fields we should have in our theorem. And you can think of a flux as being in exactly the same story as you want electromagnetism, just with higher form fluxes. And so you can locally think of it as just the exterior of some gauge potential. That can be written in terms of the structures on the Sasaki-Einstein in this case. And that's really interesting because it's telling us that we can actually insert that into the geometry. So usually in the way we think about theories in physics, we have manifolds, which is like the space in which stuff happens. And then we have extra structure on top, which are our fields and our fluxes and stuff. Here, we're going to put everything into the geometry. And in the math literature, as I'm sure you all know, A4 is just a connection on a gerb, and the F4 is just its curvature. Okay, so this is the part where we get to the generalized geometry. For whom is this familiar? Yeah? Okay, good. Okay, if it's not familiar, feel free to slow me down. If it's familiar, feel free to speed me up. So we're going to build a generalized geometry. And as I said, we're going to build a simpler one. So we're not dragging along too many times in the talk, but it's going to be based on SL6 cross R plus, which is essentially GL plus in 6 dimensions. And what we'll see is that this is dual to a Sasaki-Einstein, that this will define a Sasaki-Einstein geometry, which will be dual to a commutative algebra. And the first thing that we do is we build lots of representation spaces for it. The representation spaces that are going to be useful to us. So the first one is what we call the W bundle, and that's just a 4-dimensional fundamental representation of the SL6. And I've written its decomposition in terms of GL5. This just gives you a notion of what kind of objects in terms of vector fields, fluxes, forms on the Sasaki-Einstein manifold you need to sort of embed in this thing. So when we write our structures out properly, we'll write them in terms of objects that live on the Sasaki-Einstein or structures on the Sasaki-Einstein. And that's why I'm giving you these decompositions.
Sorry, can I ask something?
Yeah.
Is it M is 5-dimensional?
Yeah. Yeah, so you've got 5 in here, and then 1 in here.
GL5 maps to SL6.
Yeah, that's how it's embedded essentially. Yeah.
Are you assuming then spin or something so that the square root makes sense?
I'm afraid that's beyond my pay grade. Yeah. Okay. Okay, so the next structure, the next bundle that we want to define is a generalized tangent bundle, which is just the 15 bivector representation of the SL6. This one could be not so useful to us, but this one is useful, so keep this one in mind. The U bundle is the second one that's going to be useful to us, and this is effectively a three-form representation of the SL6, weighted by some factor, which has meaning in the physics, but that's for another day. So the cool thing about this is that we can define a Dorfman bracket, or equivalently a generalized Lie derivative, on the generalized tangent bundle, and it looks a bit like this. So I've got two sections of the generalized tangent bundle. I write them in terms of their GL5 bits, where this would be a vector, and this would be a three-form, and this is again another one with a vector and three-form. And the generalized Lie derivative or Dorfman bracket basically does this. So you've got the usual Lie derivative here, and then some extra bits with the forms. And the last bit on the end is the cool bit, which is where the flux sort of enters naturally in a geometric way in the process. So what we've done here is actually we've twisted the Dorfman bracket to include the fluxes, but essentially this is how the flux then appears in a purely geometric way without me having to add it as extra structure. This is compatible with the GL6 structure, which just means that I can use this Dorfman bracket on all my other bundles. Okay, so this is kind of one of the important bits. These sections of the generalized tangent bundle I can think of as generating what we call the generalized diffeomorphism group. And this is a group that is formed of diffeomorphisms and where? LVW. Sorry, yes, that should be a Y. Yeah. Yeah, I decided to change that and I didn't change it down here. Thanks for pointing that out. Okay, so these sections of the generalized tangent bundle are going to generate what we call the generalized diffeomorphism group. What is that? That is a group that is formed of all of the diffeomorphisms on the five-dimensional space and the gauge transformations that we naturally have because we've got fluxes in our theory. So in this case, it's going to be a gauge transformation by it's going to be generated by a three-form. And this is what the part the string theory tells us. So from the string theory, we told we have these fluxes, and so we know that we need to add these in the ingredients of the generalized diffeomorphism group. And the cool thing is that a generalized tangent bundle always gives us this fact that it gives us it generates the GDiff group as a whole. Okay. So the second step is to define two structures. So this is where I start to do the defining the Sasaki-Einstein manifold thing. The first one is an SL3C structure, and the second one is our SP6 structure. And together they're going to form the S3 structure in the usual way. So you've got GL3, you've got a GL6, you've got the SL3C in it, the SP6 in it, and then the SU3 that the common SU3 that they should then together define. My X, so my SL3C structure, is living in the U bundle. So that was the this is not going to be defining an SL3 structure on the Calabi-Yau. It is really not going to give me that. So what it is going to tell me is it's going to tell me things specifically about the Sasaki-Einstein geometry. And that is because these are not structures they won't be thought of as structures on W, so on the fundamental representation of the SL6. They are structures on the generalized tangent bundle, which is E here. And then the cool thing is that the space of all SL3 structures is itself scalar. with a moment map, and that moment map is going to be a moment map for the generalized diffeomorphism group. So what does this look like? Well, this is what the form that they take in terms of the structures on the 5-dimensional manifold. So again, your contact structure, your holomorphic, anti-holomorphic 2 forms. You've got your potential Reed vector fields here, contact structure, Kähler 2 form. Imposing integrability conditions yet. And the twisting of the generalized Lie derivative, or the Dorfman bracket, does something really useful for us here, is that it basically means that Lie derivative with respect to K becomes, or the generalized Lie derivative with respect to K becomes the Lie derivative with respect to the Reed vector field on a 4-dimensional manifold. And so we can see that LK is basically an isometry generator for our 4-dimensional space. So it really is telling a 5-dimensional space. So it really is telling us something about the Sasaki-Einstein, not about the current geometry. And there's a natural action of our SL3C structure on the generalized tangent bundle. And so if I complexify it, it gives me a decomposition in terms of positive 0 and negative eigenbundles, decomposing the 15 into a 3, 9, and a 3 bar. So X really behaves like a complex structure on the generalized tangent bundle in sort of the same sort of way as we think as the SL3 structure, and the usual complex story is Kähler story as being like a complex structure on the tangent bundle, or complexified tangent bundle. It's the same idea. One more detail that we're going to need, and then we'll start talking about how to make some integrability conditions, and that is a metric. So we have a 3-form invariant of the SL6 that we can define, which takes in 3 copies of the generalized tangent bundle and maps you into something in the determinant bundle. And we can use this to define a metric on the generalized tangent bundle. And we do this by recognizing, first of all, that there's an isomorphism between the tangent bundle to, or the tangent space to the space of SP6 structures at any particular element of the generalized tangent bundle and the generalized tangent bundle itself. So I'm going to pick an element that's in the 0 eigenbundle. And the reason that I'm going to do that is because I'm going to use this to make my metric. And so overall, it's going to map me to an element of the determinant bundle that I'm then going to integrate over. It's going to be a scalar. I don't want it to be charged under the SU2 generated by my by X. And so I'm going to start with something neutral so that then I can generate something that's charge neutral out the back here. Okay, so a metric would be obviously taking tangent space for the reals, and we do this in the following way. And thanks to that, we can define a dual to objects in the generalized tangent bundle by just sticking one in the first entry. And conversely, I can define a dual of the dual, which I'm going to say is just an element of the tangent bundle itself. And I'm going to denote those by hash. Okay, so what are the integrability conditions on these structures, and how do they reduce to the Sasaki-Einstein ones? Well, first I have this compatibility condition, which is going to give me the usual compatibility condition on the Sasaki-Einstein. I have an integrability condition, which gives me the closeness of the K2 form. The Sasaki condition comes from the moment map. The integrability condition on the holomorphic 2 form comes from the Reeb condition on the X structure. I've got the normalization, which boils down to the normalization that we inherit from, that we would have inherited from the point if we thought about it that way. And we get the flux, so what the flux should look like in terms of geometric objects. And finally, the all-important one is the involutivity condition on the L plus bundle. So this is equivalent to the closeness of the Cauchy-Riemann structure. Remember this is part of the eigen decomposition with respect to X. So
can I ask, are these F terms and D
The moment map condition corresponds to a D term. Yeah. And the F terms come in the evolutivity. Okay, so we can actually boil all of this down to pretty much two conditions. And that is the involutivity condition, which gives me the Cauchy-Riemann condition. And then the moment map condition, which I can equivalently write like this by just substituting this into that. And that gives me the Reeve condition and the Calabi-Yau normalization. So that was why we're interested in describing things in terms of context. So all I really need are these two conditions to be satisfied. And then I have defined a Sasaki geometry using generalized geometry. So what was our first question? What is the dual to these non-commutative algebras as a geometric structure? Well, I showed you a commutative one, which was the SL6 in the language of generalized geometry. Embed that into the exceptional groups, and you'll get the non-commutative algebra. The second question is, what is the dual of a-maximisation for these non-commutative theories? Again, I'm going to use a simple example, but it all embeds into the exceptional. And the reason we're going to be able to answer this question is because we're going to use generalized geometry in geometric invariant theory. Yeah. By regular. Oh, in that sense. I think so. I think you should be able to tell whether or not you have regular, quasi-regular, or irregular. Well, yes, you would, because it would tell you which Sasaki-Einstein you have. And this will tell you which Sasaki-Einstein you have. Okay, so we have a group action of G-diff on a Kähler manifold that has a moment map. And we have this thanks to supersymmetry. And pain usually in defining moment maps and doing GIT with things where you want to include the whole of the diffeomorphism group is defining a norm, but the algebra of the diffeomorphism group isn't so obvious. Well, going to G-diffs, you get one, as I showed you earlier, you get the metric, which is really cool. That's what Susie gives you. Okay, so generalizing gradient flows. So just to repeat, these are the two conditions that we needed to define the Sasaki-Einstein solution, right? Okay, so the step one is just to impose the first condition. So the involutivity condition, I'm just going to impose. And I'm also going to project space. I've got within the involutivity condition, and I projectivize it. So Z hat is Kähler, up to caveats we can talk about later. And it has a moment map on it, and that moment map is a moment map for G-diff. And then the second condition is given to us naturally by using Cohen stratification. So we can define the norm squared function using our invariant. And when we do so, we find a critical set. So we vary the norm squared function, we find the critical set, and we know that the image of the critical set under the moment map gives us a set of G-diff orbits in the dual algebra. For us, what this equation means is that either the moment map vanishes in the usual story, or that this is satisfied, which is essentially the generalized geometry way of writing that the gradient of the norm squared function vanishes for non-zero values of the moment map. It's the same story. Now, because we've projectivized, we are looking at X as being a representative of a whole C, whole complex plane. And so we can put whatever constant we want out the back here. It doesn't have to vanish, and you still stay on the same point. And so we're going to choose 3 because, as you saw earlier, that's the 3 or 3i, because that's the 3i that we want for our Reeb condition. And then we define a set of representatives for each of the types. And we are going to say that the stratification of Z hat is then given to us in the usual way, which is just a decomposition of Z in terms of all of the points that flow under the norm, the gradient flows of the norm squared functions to a critical surface whose image under the moment map is lambda. So that's the usual story of the curve-ness stratification. The cool thing is that we get the second condition out. And it seems like a big statement that we could, you know, actually really define the stratification because of how big the space is and so on and so forth. But physics kind of tells us that we're right. So as I said, we are interested in the unstable flow, so the ones where the moment map doesn't vanish, because that gives us the second condition. And so, yeah, what we find is that going to a point on the critical surface that is an unstable point brings us to a solution of the for our structures that give us a Sasaki-Einstein geometry. So we basically flow to an X that satisfies this condition, and we didn't. And what we're also finding, therefore, is that the Lie derivative with respect to mu hash on the critical surface is the Lie derivative with respect to the Reeb vector field. So it's giving us the Reeb vector field. And the other important thing to note is that as as we flow along the gradient flows, so the gradient flows of the norm squared function are complexified diffeomorphisms, or can be thought of as complexified diffeomorphisms. And so what we're effectively doing in the stratification process is we're defining a Reeb vector field that corresponds to an equivalence class of X under G diff C. So what did we just show? We just showed that you can use coordinate stratification to find solutions to define the structures on your Sasaki-Einstein geometry. So to find Sasaki-Einstein solutions to your integrability conditions. And the next thing I'm going to do is then show how we can then go further with this and use this and the notions of GIT to define the dual of this a-maximisation problem, which is in the geometry the equivalent of finding the Reeb vector field that gives you the Sasaki-Einstein geometry. And this is a big mystery in physics, particularly in CFT, especially in the case of these where for us, our CFTs are described by non-commutative algebras. And so let's show it.
Sorry, before you do that, could you go back? So the unstable guys correspond to Sasaki-Einstein geometries?
Yeah. And
the stable ones correspond to?
So the moment map vanishes. So on the face of it, it looks like we might be getting Minkowski-type background. So the involutivity conditions for Minkowski solutions would have a vanishing moment map. But actually, it doesn't tell us anything about the SP6 structure, because that drops out of this whole process, right? I've got no way, if I don't have the moment map condition, I've got no way of linking K to X in this way. No. Yeah.
So this isn't like, you know, with when you try to minimize norm square scalar curvature in Taylor geometry, you go to the stable guys correspond to constant scalar curvature.
Mm-hmm. Mm-hmm.
That's a generalized equation, but it includes a vector field.
Okay.
So it kind of looks a bit like
it does kind
your unstable guy.
Yeah.
Yeah, I'm not sure where this is going. Sorry, I'm just curious. But if you keep scaling them back down, are they converging to something, some special type of geometry?
Okay, so to answer the a-maximisation question, I'm first going to have to establish the notation. So now we're going to move more to the Hesselink picture of the stratification. So first of all, I need the reduced moment map, which is basically just to take the moment map, you subtract off one of the generators of the algebra, and you restrict that moment map to the commutant of that generator in the group, modulo the U1 generated by that generator. And so this basically becomes a moment map for this group on some restricted surface of hypersurface of your manifold. And then I can define another norm squared function, which is going to be my reduced norm squared function in the same way as I did the first one. And then I'm going to define what we call the Hilbert-Mumford slope, which I'm sure you're familiar with. And it's defined in the following way. So I pick a generator, I pick an X, I make that X flow along a complexified orbit under this generator until it hits an invariant surface. And then I evaluate the perfection of that moment map with the generator that I picked, normalize it out, and I get the Hilbert-Mumford slope. And literature tells me, so mathematicians have told me, that this thing is maximized. So if X is unstable, then I can maximize this thing, and it's maximized at some generator that is precisely the representative of the stratum that X belongs to, a representative of the stratum that X belongs to. So this is effectively a way of determining, maximizing this guy is a way of determining what this lambda is that's supposed to characterize this stratum. Okay, so how do the flows work? To be really pedantic about it. So if I've got here the flow that I would get from the first norm squared function that I defined, and it flows me down to the critical surface, then in the Hesselink picture, I'm maximizing the Hilbert-Mumford slope if it's unstable. Still talking about the unstable people here. And then I flow along its complexified orbit till I hit this invariant surface. And then I use the reduced moment map on that invariant surface to define a norm squared function whose gradient flows will then take me down to XC again. This is just two alternative paths to the same place. We know that the Hesselink and the Cohen-Ness stratifications agree. And so maximizing the Hilbert-Mumford slope is essentially for us finding the generator or the corresponding generalized Reed vector field that will determine our Sasaki-Einstein solution on the critical surface. And so that's what the jewel of a-maximization is in the geometry. And of course, if you embed this into a larger generalized geometry, then you get this for geometries that are dual to the non-commutative algebras. So to summarize, what were our two questions? So the first one was, what is the dual geometry to a non-commutative algebra? And we claim that you can define these geometries using generalized geometry and the help of some string theory by defining exceptional generalized geometries. So generalized geometries based on the exceptional groups. We also saw that we could use the moment map on the space of SL3C structures, or in the exceptional generalized geometry, it will then be a space of SU*6 structures to define a stratification, and that the critical surface for unstable orbits, unstable flows, corresponds to Sasaki-Einstein manifold solutions. The second question we asked ourselves, technology doesn't die on me, there we go. The second question we asked ourselves was, what is the dual of a-maximization in the dual geometry? And so essentially this was just giving you an example of what we can do with this stuff. And we found that it was extremizing the Hilbert-Mumford slope. So this is now generalizing this idea of Sparks, Martelli, and Yau volume minimization. We can now do this for all sorts of manifolds. And of course, we can generalize this, but in the exceptional groups, move to other dimensions. The story, well, moving to other dimensions, we hope, but at any rate, in 6 dimensions, it's definitely the same story. But yeah, feel free to ask me about that later. And now I'm gonna finish by asking you a question, which is again motivated by physics. In physics, we have this thing that we call renormalization group flow, which is effectively what happens when you define a theory at a very high energy. You then watch it cool down, and we call that flow, to a very low energy, and you watch how the degrees of freedom of the theory change and all the different processes that might happen, what the differences between the UV theory, so the high energy theory, and the IR theory are. And we want to understand what this renormalization group flow looks like in terms of the geometry. Renormalization group flow, of course, applies to theories. And so in the physics, we're comparing different CFTs. So it's the algebra side. Now, we know that in generalized geometry, this renormalization group flow corresponds to what we call the domain wall flow equations. And they're effectively similar to the Sasaki-Einstein conditions, except that you get rid of a couple, which is the Reeb condition and the moment map condition, and you end up with these two things. And R is the flow parameter. You can think of as a flow parameter, so nothing to do with the R of the homothetic vector field. So our question for you is, say I had just some space with some Hamiltonian group action on it, times or crossed by the dual of the algebra of the group that acts on it. Is there a function of, well, in this case, x and k star, such that the gradient flows of this function correspond to our domain wall equations? The sort of thought, which is mainly thanks to my supervisor, is that it might well be, that's all things are, is that it might well be related or may even be the Hilbert-Mumford slope itself. So you can see that if we vary it, we start to get something that looks a bit like this, and then something that looks a bit like this. It's starting to come close to the domain wall flow equations. And then the expectation would be that if we reduce the domain wall flow equations by fixing k or x, we would end up getting the integrability conditions for the Sasaki-Einstein. And yeah, so could we use this to flow both the scalar and the complex data simultaneously in order to find solutions instead of just having to fix the complex and then flow the scalar? And of course, related to physics, this would tell us a whole bunch of stuff that we're really interested in knowing. So that's the question for you. Yeah, the end. Thanks for listening, and please help.
Great question at the end. We just have an abstract. Can we go back to the question?
Yeah.
We have an abstract space N acted on by a group G.
In a Hamiltonian way.
What function on there? What abstract? So let's suppose we know nothing about the normalization.
Sure.
And we know nothing about your specific example.
Sure.
What properties do you want this function?
Say I guess the way that I sort of see it is that if it should reduce to, I would think of it as reducing to the flow of the norm squared function if I projected out this part, which is to say that I actually don't allow anything to flow in the group, in the algebra bit. So if I'm just looking at the story on the manifold N, then I'm thinking of norm squared flow, blah.
So N is scalar, probably?
Yes. Yeah.
And then if, let's sort of choose a billion or something, you take on slices of N times Y vector.
Yeah.
You want this function to just be the norm square of the Hamiltonian.
That's kind of how I would picture it, yes. Yeah. I mean, I guess you could take your pick, but essentially because we're linking it back to this moment map story, and if it will allow me. Probably too far back. Yeah, so the flow on like the critical surface is given by this, the norm-squared function of the reduced moment map, right? And so we're effectively looking for the point where this thing vanishes, because once you go to the critical surface and you flow into this norm-squared function, you're actually looking for x's that are stable under this sort of substratification. So we want this to vanish. And so what we're really saying is like, this is a function of my x's, and I want this to flow, and I want this to flow. Instead of just saying, okay, I'm kind of fixing that this is going to have to be equal to something, and I flow this. So this, you know, I'm saying it's going to become my reap, and I just allow this to flow on the complex space. So that's why dual. But essentially,
so the one thing is get a flow that by checking.
excellent question. I guess I don't know, because the only intuition that I have for that would be this physics motivation of the renormalization group flow. I think it'd probably be easier if I just did it this way. So that would be this, right? So you're saying if I fix x, yeah, then I'm essentially saying that k is, or k star is flowing like minus k star plus a constant. It's not hugely interesting. Okay. Yeah. No, do. Yeah. Which one do you want? With the question on it, I think is probably further along.
So one thing that I kept seeing is that this G dual, I got the impression the value that you would have shifted by. You're translating mu minus K dual. Whereas here it looks like you've evaluated. It looks like an element of the algebra. It looks like evaluated.
So you are
So we don't want to be thinking about mu minus this element of G dual.
No, this becomes a variable.
Because on previous slides there was some mu minus K dual.
Yeah, and that's
not what we're thinking.
No, so in the previous slides where I was subtracting out or giving you a K, what that was really meaning was, so I go to some, I did it better in the algebra actually. So when I define this, for example, so I've got here, like I've just defined what the restricted moment map is going to look like. I'm picking some arbitrary psi. And then I'm saying that's due to some arbitrary k star. He's not at the solution. Yeah, this gets confusing.
I'll ignore that. So if we think of this, the algebra dual as just the algebra.
Yeah.
Then you want to evaluate mu on that algebra. proposed function for the new one you want?
Oh yeah, good point. Yeah, because otherwise.
Somehow, I just act on X, not on N times G.
So the idea is that we're really thinking about, okay, take the commutative case. You want to define, okay, so you have a Calabi-Yau cone. You have a Calabi-Yau cone, let's say Calabi-Yau 3. Calabi-Yau 3.
Oh.
Yeah. And you take, you want to define complex functions on it, polynomials. Then you have three coordinates. Thank you. 3 coordinates. And those would be your holomorphic coordinates, right? You can then make polynomials out of these coordinates. You can make the polynomials in any order that you like. Now let's assume for a second that these things, you don't really know yet that they're polynomials. You just know them as kind of 3 letters. And the polynomials is just like an alphabet that you make, a set of words. You can make any string of words that you want. You can then, so the idea behind Ginzburg's work was to say, okay, I'm going to now define a potential, which is really just another set of words. I'm going to vary that potential with respect to each of the field, and that gives me a 2-sided ideal. Effectively, what it's telling me is about whether or not these coordinates can commute, whether there's some algebra or something. And you can, in the simplest case of the Calabi-Yau 3 cone, you can, when a Calabi-Yau 3 in general, you can then think of the space of functions on the cone, space of polynomials, as just being defined by these words, quotiented out by that 2-sided ideal. Now, the polynomial, the potential that you're going to choose to describe this Calabi-Yau geometry is going to be a potential that gives you commutation relations. It's just going to tell you that all your coordinates commute. So you just get, the algebra is just polynomials with multiplication. And so that's kind of the idea of the algebra. Then you've got the Calabi-Yau as the geometry side. But we think of the Calabi-Yau as being a cone over some linked geometry. So you could think of it as a cone over an S5. And so we think more of the dual geometry as being the S5. Because we're interested in kind of linking it to, well, the idea is kind of inspired from the ADS-CFT picture. And in the ADS-CFT picture, we want to decompose our gravity space into a 5-dimensional ADS, and then a Calabi-Yau, and then a Sasaki-Einstein, 5-dimensional Sasaki-Einstein in this case. But if you take different limits of the geometry or look at the geometry differently, you can then think of it as a 4-dimensional space in a Calabi-Yau cone. That's entirely sort of the picture that you choose. But for us, we want to think of the Sasaki-Einstein because we want the dual ADS space, the ADS space. And so that's what I mean by the duality. So you just take these letters, some two-sided ideal, and that corresponds to some geometry. And I can do that for any potential and generate like these algebras that, you know, maybe your coordinates won't commute. Maybe you'll have some special relations, and then you can do cool things like generate, I don't know, the Lie algebra of SL2R or something. And then that would kind of be dual to an SL2R manifold, I guess. Welcome. Welcome.